So hello, welcome back. We have a kind of very short agenda for today in which we will be giving in the final touches to genetic programming, and we already know that the last topic that is left out in the entire discussion on genetic programming is wherein we use some kind of loopholes of the tree-based architecture, and we will solve it using a linear technique that is known as a grammatical evolution. Now, since this is an invariant of genetic programming, all the concepts exactly alike copied from the genetic programming to the grammatical evolution. So ultimately I'll have a program, I'll try to evolve a program across generations. I'll try to evolve it across generation from one generation to other. I'll use the same evolutionary operators to evolve, to generate a higher generation population from a lower generation population. I'll use the same evolutionary concepts, but this time I'll not be working over a tree-based representation of a program. I commented out in the previous couple of hours of lecture that the tree-based representation by its very virtue happens to be a very easy kind of representation for me to work upon. It happens to be a very easy representation in which I could easily adapt my program onto a tree-based architecture. But unfortunately, the tree-based architecture had got in some kind of limitations that I could not use the conventional genetic algorithm operators, in which I had to adapt my own operators to work over a tree-based structure. I had to make in some kind of amendment so that they worked over a tree-based architecture, a tree-based structure, and based on this I carried forward the complete evolution. So here also there would be some evolution that would happen, but this evolution would be on a linear representation of a program, so that I can use more or less my genetic algorithm operators, my genetic algorithm fundamentals, which are really very simple to handle. Because of a nice little string representation, they are very simple to handle. I'll use those operators, and how will I carry forward the task of representing my program into a linear architecture is by using this term known as grammar. I'll use some kind of grammar in order to convert my program, in order to convert my code that solves my problem into a linear architecture, into a linear string of integers. That is where I use the term known as grammar. Now, grammar, again, the word comes from simple languages, it comes from natural languages. And in natural languages, we've got the concept that grammar specifies the rules, the syntax, the do's and the don'ts, in which you can use the different words. A grammar has multiple concepts. It has got phrases, it has got subphrases, it has got nouns, it has got verbs. How these are connected to each other and what role do they play with each other in order to generate a complete English sentence or any sentence of any language, what are the rules? That is specified by this grammar. The various concepts, they are all specified by this grammar. And as a result, we get as the end product the sentences of the natural languages. The sentence, the grammar of English will be different from that of Hindi. So the basic architecture, where the various verbs go, where the various nouns goes, would be different across the two languages. And if I use the Hindi grammar for generation of Hindi sentences, I'll get in grammatically correct sentences of Hindi, and likewise for English. So the basic pattern is that I am using the concept of grammar borrowed from the natural languages, and I'm using them for the evolution of my code, for the specification of my individual. Now again, whenever I say the word grammar, I've said that the only major change that I will be carrying across is an individual representation. The only change we will have would be in how we represent an individual. The other things would more or less be conventional in nature. We might give a very brief discussion over it. So we are only carrying out a change in individual representation. And how do I represent my individual? For that we are using a syntax, we are using a set of rules that is known as a grammar. Now the moment I say grammar, my grammar is always constant for the language in natural languages, and in a similar sense whenever I use the word grammar over here, my grammar is constant to a problem. Every problem that I use over here will have its own set of grammar. It will have its own set of grammar, and when I say that it will have its own set of grammar, that means all the individual of any population of any generation, all the individuals of any population, any generation, they obey the same grammar. And since they obey the same grammar because they are solution of the same problem, there is a part of solution that is common to all of them that has already been specified, and all I need to do is how this grammar is used. There is an architecture that is already specified. How this architecture is used is what is to be worked upon, and that's why grammatical evolution sometimes results in smaller individuals than what might be normally expected when you vary everything. It normally results in more compact, more smaller individuals where only specifications on how this grammar is used is specified into a linear architecture. The grammar part of the individual, it's centric to problem, it's constant to problem, and that remains intact for all the individuals, for all the generations. So my only problem right now is that how do I specify the set of rules, and how do I specify not only the rules in which I would be using the program, but also in how do I represent the various terms and concepts, and how I define the various terms and concepts. That is what would be defined by grammar. And my individual would be nothing but how this grammar is to be used. Grammar is normally defined by what is known as a Backus-Naur forms, or the BNF. Now again, in programming languages you might have studied that the BNF form is a very simple form in which I can specify any programming language. I use a similar concept over here. I use exactly the similar concept over here, where I'll be using the Backus-Naur form to specify the grammar of the program of the problem that I'm trying to solve. I'll use this term grammar over here. So the grammar for any language by this form is represented by a set. The grammar is always represented by a set. This set contains specification into what are the non-terminating symbols. I call them as a B. So similar to languages where I had noun verbs, so there would be a lot many symbols, a lot many concepts involved. Any symbol that is a part of the final program is known as a terminating symbol, and any symbol that is not a part of the final program is known as a non-terminating symbol, and non-terminating symbols are always changed to the terminating symbols. So there is a non-terminating symbol and there is a terminating symbol. My entire class of symbols is nothing but a union of terminating and non-terminating symbols. Terminating symbols are the ones that are part of the final program, and non-terminating symbols are the ones that are not a part of the final program. They represent sub-programs that will ultimately be evolved later, or that will ultimately be replaced later with time. I have in operations known as production rules that carry forward the conversion of non-terminating symbols into a set of terminating symbols. I have got in operations known as P that convert these non-terminating into terminating symbols, and they might additionally convert the non-terminating symbols into more number of non-terminating symbols, into less number of terminating symbols, anything based on these rules. So I got non-terminating symbols, I got terminating symbols. I can never give my final output a non-terminating symbol. I need to give as my final output only and only a terminating symbol. So I needed some mechanism that will convert my non-terminating into terminating, and that is by these production rules. And there are mechanisms by which I need to see various combinations possible, various combinations between the various symbols possible, for which I convert non-terminating into a set of terminating and non-terminating symbols. And every grammar starts with a discrete symbol S, so this is known as a start symbol. Whenever I work with grammar, my general guideline is that suppose I need to construct a sentence, I'll have some start symbol. Let me say the sentence itself. I'll apply a set of rules to see how this sentence can be broken down into combination of nouns and verbs. I'll further see in how these nouns and verbs can be further broken down into sub-phrases. So there's a noun phrase, there's verb phrase, I'll try to break them down further into sub-phrases. I'll make them further break down into sub-sub-phrases. I'll ultimately towards the end substitute with words, and that is what becomes a beautiful English sentence. That's what becomes a beautiful English sentence, balanced as per syntax according to these rules, having only final English words as the final terminating symbols, and in the meantime we use a lot of non-terminating verb phrase, noun phrase, and these expressions over here. So the various architecture, a sentence can be active, it can be passive, it can be a mixed both. That all depends on how these rules are being used. For the same non-terminating, I can use different set of rules to generate some different sentence architectures, and they all give me different sentences. So that is what we get from the concept of English language or the natural languages. The same concept I try to see if I can generate in programs to do this. So in order to do this, I've taken a very simple example. Let me say my problem is that I need to write down the grammar. I need to write down the grammar of the generation of a Boolean expression. I need to write down the grammar that generates some kind of Boolean expression, and how am I going to write down this grammar? So let me say my grammar for the generation of Boolean expression will be nothing but non-terminating, terminating, production rule and start symbols. Here my start symbol, here my non-terminating symbols are nothing but expression. It is nothing but an expression, a binary operator, a unary operator, a left bracket, a right bracket, and I guess that's all. These are what are my non-terminating, these are not the non-terminating systems. A binary operator, a unary operator, these are what are the set of non-terminating symbols. These are what are the non-terminating symbols. I'll introduce another non-terminating symbol known as a Boolean value or a bool. My terminating symbols are a true, a false, all the various operators, so that means an and, a or, a zor, a nand, a nor, a left bracket and a right bracket. These are my set of non-terminating symbols. Now it can be seen that any kind of Boolean expression, be it true and false or true, or any different combination, it contains nothing but all these symbols that I were written down over here, and apart from that it does not contain any other symbol. There's a note I forgot. It will always be a collection of these symbols over here. So these are what are the terminating symbols. My production rules. So I specify non-terminating and specify terminate. The start symbol is nothing but an expression. I start off with some kind of expression. The start symbol is simple, it's just an expression. It is only and only an expression. So that's what I write out over here as the EXPR, the expression. I'll start off with that expression and I'll apply a set of production rules to convert this non-terminating start symbol into terminating symbols. Now start symbol, it is usually kept non-terminating in nature because if its start symbol is terminating in nature, my entire grammar can model only one thing. My entire grammar can model only one thing, and that is the start symbol as well. The production rule, they always carry forward the replacement of non-terminating with a set of terminating or non-terminating symbols. I need to always start with the start symbol. If this is terminating, I cannot apply any production rule over it. So coming up onto the production rule, I'll use some kind of matching between non-terminating to the terminating. So I'll say that an expression can be broken down into a bracket, expression, a binary operator, and an expression, or it can be broken down into a unary operator and an expression, or it can be broken down into a Boolean value. So that is where the expression I've broken down. I've broken it down using either a binary operator, a unary operator, or a Boolean operator, or I'll just replace it by a Boolean function. This is how my expression broke down into. My binary operator is nothing but that can get replaced by an and. I have this or this or this. My binary operator, it can be either and, or it can be or, it can be not, or it can be NAND, or it can be XOR, it cannot be not. NAND, NOR, and XOR. My unary operator will ultimately get broken down into a NOT. That's the only unary operator that I have. It will always get broken down into NOT. My bool can get broken down into either a true or a false. These are terminating, this is terminating, this is terminating, or these are terminating and these are not terminating. So expression is being converted into a set of non-terminating symbols, and all the other are converting to a set of terminating symbols. Sometimes we get a mixed mode, some terminating and some non-terminating. So that is what I specified as a production rule. That is what I specified as a production rule. So let me again generate out the expression true and false or true. Let me again try to generate this sentence using this grammar. So I first start off with expression. This is what my start is. I start off with expression. Then I say I need to apply some rule. I need to apply some kind of rule. So let me apply the production rule. That expression is changed into expression and expression by the application of this rule over here. Let me say this is how my application, my expression is changed it into expression and expression out like this. Then what I do is that I keep this, I say this is an expression, it can be converted changed into a bool. At the second step, I change this expression into a bool. In the third stage, I just change this bool into true. In the third stage, I change this expression into a bool. So I've got some part of it already there. Now what I do is that I change this expression. I divide it further using the same set of Boolean rules. So I say it is true and expression, I change it into expression, bio expression. I forgot the step over here, there had to be a step, expression, bio expression, and then the expression will convert to and. Here I use expression, bio expression over here. That is what I use. Expression being converted into expression, bio expression. The next time this expression will change into a bool. This bio will change into a or, and this expression will change into a bool, and this will ultimately get replaced by false, and this will get replaced by true. So I can see that I can generate any kind of sentences starting from my expression based on the same production rules. I can generate any kind of sentences based on the same production rules. So that is one part of it has been done, an important part that I have already done. And that important part was to generate in a grammar. I have already done the part to generate in a grammar. So that part has been done. Now I need to work further with my genetic algorithms with a linear representation. Let me for some point of time assume that I had a strategy in which an expression over here, a program in general case, or an individual can be represented by nothing but a set of integers. Let me say that there was a technique by which a program could be converted into a set of integers. Let me say this was x1, this was x2 up till xn. Let me say this was x1, this was x2 up till xn. Let me further assume that I devise in some kind of fitness evaluation of this individual that returns me fitness. So all I want to say is that if I have these two assumptions intact, that there is some way in which the individual is represented in form of a series of integers and I have got some fitness evaluation, I'll be able to generate this individual randomly by all random numbers from x1 to xn. I'll be able to generate it up randomly. So initial population can be defined for all n individuals, or let's say for all small n individuals. I can have some kind of individual representation. I can have some kind of population that is defined randomly. I can write down some kind of stopping criterion. That was my other requirement of the genetic algorithm. I can carry forward selection. Assume that the fitness is known. I can carry forward selection. I can carry forward mutation because it's a normal integral representation. So I will follow all genetic norms. The real number representation of the genetic norms. I am using the real number genetic norms. So using the real number representation of the genetic algorithm. Similar to that, I can carry forward mutation. Similarly, I can carry forward crossover. Using the same principles of the genetic algorithm, I can carry forward mutation. In the similar way, I can carry forward crossover because all these are nothing but a simple genetic algorithm individual. All this is nothing but a genetic algorithm individual. I can carry forward elite. The best individual gets promoted. So based on that, my complete genetic algorithm architecture is intact, it's working. The only thing is that I need to consider how do I calculate fitness of this individual. and that means the only thing I have to do is to convert this individual into a program. The only thing I'm supposed to do is how to convert this individual into a program, because how do I calculate the fitness of a program is something that we've already seen in genetical programming. And how do we calculate the fitness of a program? We have already seen into genetic programming, and how do we do that? So if I am able to convert this phenotype, genotypic solution into some phenotype, my task is done. My task is completely done if I am able to complete this genotype into some phenotypic solution. And that puts us across a very interesting fact, is that earlier we used to say in individual representation we need to make sure how this phenotype would get converted into a genotype, and the genotype would get reverse converted into a phenotype. The conversion of a phenotype solution to a genotype solution, it is never called in a genetic algorithm. I never do that. I generate the individuals randomly, and only to get the fitness I convert them into the phenotype back. I never convert the phenotype into a genotype. So I only need a strategy in individual representation technique. Since we are dealing with the genetic algorithm, everything we discuss except for the individual representation technique, the other things are same. The only thing that I need to discuss, is the fact how this genotypic solution will get converted into this type of phenotypic solution. So this is the genotype, and this might be the corresponding genotype. All we have to carry forward is this conversion, and this conversion is carried forward based on the grammar that we have specified. It carries forward based on the grammar that we have specified over here. Using this grammar, I have to convert this representation into this representation, and the other part of it, the genetic algorithm, it would behave normally in nature. So in order to do that, I make in one addition to the grammar, I make in an addition to the grammar, I make in a table. I make in a table where I have the non-terminating symbols here, and I've got the number of rules that they correspond to over here. So my non-terminating symbols here are expression, biop, uop, and a bool. These are the 1, 2, 3, and 4 non-terminating symbols over here. I write down them as the left of the table. Expression, it can be either replaced by this, or it can be replaced by this, or it can be replaced by this. So I have 3 choices in which I can exchange my expression with any one of these 3. I have got 3 choices. So expression has 3 choices of replacement. I can say expression is expression, biop expression, or I can say expression is uop expression, or I can say expression is bool. I have got 3 choices. So I write down 3 over here, the number of choices that I have. My biop has 1, 2, 3, 4, and 5 choices. So I say my biop has 5 choices. I can replace my biop by an, or, nat, nor, and, zor. I've got a total of 5 choices. So I replace my biop with 1, 2, 3, 4, and 5. These 5 choices. So there's a number 5 here. For uop, I have got only 1 choice. Anytime I have got uop as my choice of replacement, as whatever I need to replace, I'll only be able to replace it with not. So I've got only 1 choice with me. And for bool, I have got 2 choices, either a true or a false. I've got some 2 choices there, a true or a false. So for bool, I have 2 choices over here. Whenever I get bool as my non-terminating symbol, and I need to fire some production rule to convert this non-terminating symbol into whatever terminating or non-terminating symbol, I'll have 2 choices with me, a true and a false. So 3 choices for expression, 5 choices for biop, 1 choices for uop, and 2 choices for bool. The mechanism in which I convert my genotypic solution, which is nothing but a string of integers, the mechanism by which I convert my phenotypic solution or a bit of integers into the corresponding expression out in this case is exactly the same as the example that I took. I'll follow exactly the same pattern as the example that I took, where I generated some kind of true and false or true. I use the exactly same mechanism. The only thing is that after every step I had some choices to make. After every step I had some choices to make. I said that replace expression by this thing. There were a couple of choices that could be made. And the selection of my choices was done based on the final expression that I had. In that case, here it would be done based on the individual that I have. So here we'll see how we can use this table and the set of production rules in order to get that individual. So I will go with this. I will keep this table alive. I will keep it on the board, and we will take in a general expression. We will always take in an individual. Let me say 5, 7, 8, 9, 10, 12. Let me take this small individual, and we'll see how is it that using this table and two set of production rules we can convert them into a phenotypic solution. So I always start up with expression. I cannot help anything. And this is what is the first non-terminating symbol. Now again, to repeat, rules are always fired for the non-terminating symbol. So this is what is the first non-terminating symbol. I implement a counter over here that starts with 5. Now expression can be replaced by any one of these three rules. There are three rules written over here. It can be replaced by any one of these three rules. The rules were nothing but an expression, expression, u expression, and a bool. They were nothing but these three things. So I need to make a choice now that expression in the next stage can be replaced by any one of these three. Which one do I select? So for this I use this number 5. Now it is number 5. So I'll compute 5 mod the number over here 3. 5 mod 3 comes out to be 2. So I use the second rule, that is u of expression. I'll convert this thing into u of expression. That is my first step. Now I go further. This was my first step. That was guided by 5. I increase this counter up 1. I come up over here. I again find out the first non-terminating symbol. The first non-terminating symbol is here, u of. My u of has got only one choice, and that is a not. So in order to select one out of these one choices, what do? I use the guiding principle of the 7. So I calculate 7 mod 1, and 7 mod 1 is nothing but 1. So I select the first choice over here, that is not. So I replace this u of by not and this term by expression. I go still further. I increase this counter by 1, I go up to 8. My first non-terminating expression is this. I say my expression needs to be replaced by any one of these three choices. To replace expression, I have three choices. It needs to be replaced by any one of these three choices. And to select that, I use the term 8. So I calculate 8 mod 3, and 8 mod 3 comes out to be 2. It comes out to be 2. So I use the second expression over here, the second choice over here. The first one was a bio, the second one was a u of. So I'll again replace it by a u of expression over here. I increase this pointer 9. I'll go for the first now. It 9 mod 1. Europe has got only one choice, so I'll do 9 mod 1. 9 mod 1 is nothing but 1, and that means this will be converted into a not an expression over here. I'll go up to this 10. 10 mod 3. I have got 3 choices to replace this expression. 10 mod 3 is nothing but 1. So I'll go with the first choice over here, and that is a Europe. So this will become not expression biop. The first choice was a biop expression. This was the first. I'll again go with the first non terminating. Now it's 12. Three mod 12. 12 mod 3 would be 0. So I take in the last choice. I take in the last choice available. And the last choice available is bool. Now sometimes we start numbering from 0. If I had started numbering from 0, I would have taken the first choice. But whenever I got the remainder, I would have taken the second choice. And sometimes we start numbering from 1. If I start numbering from 1, if I get a 0, I take in the last choice. So that's a little bit of invariance that you can get. My 12, it will give me a Boolean expression, or it will give me a Boolean expression, and that's why when I'll replace this by a bool, a biop, and an expression. Now ideally the individual has exhausted, but my expression has not exhausted. So there are two things that I can do out here. There are two things that I can get out here. The first thing that is normally done is that I increase my pointer to the first position. So I'll again have 5. And this we do twice. So once we iterated, if by chance I get in a set of non-terminating symbols, so maximum of once we'll update the pointer to the start position over here. So once I do that, I again get 5. Boolean has 2 options. 5 mod 2 is 1. So I replace it by true. The first choice was a true over here and a false over here. Now this is the first expression that I've got biop. The first non-terminating expression I get 7. 7 mod 3 would be 1. So a biop has got 5 choices. A biop has got 5 choices, that is and, all, NAND, NOR and ASOL. So 7 mod 5 would be 2. So I'll replace this by all. Now my first expression would be this. After 7 I'll go to 8. 8 expression I've got 3 choices. And by chance it happens to be Europe. So like this I'll complete this tree, but if the second time also I do not get my final expression, suppose after this complete tree I got this as my expression, there will be a Europe and an expression over here. Then what do? I replace every non-terminating symbol. I do not go further, I do not iterate once more, because there is a possibility that I keep on iterating indefinitely. Program keeps on taking indefinite architecture, it keeps on taking complex architecture. So after one iteration, if I do not get in this final symbol consisting only of terminating symbols, if I do not get that, I replace every non-terminating by a default value. So let me say Europe was replaced by a default value of NOR, not, and expression was again replaced by any default value. Let me say that is true. I replace all non-terminating by some kind of terminating default values. So this is the final symbol that I get as, now this is a complete symbol. I have converted in a phenotypic into a genotypic into some kind of phenotypic solution based on this grammar. And based on that, whenever you do again and again, we can get some kind of expressions over up. The first anomaly that we saw over here is that after one iteration, the algorithm did not, this expression did not terminate. So we had to carry forward another expression, another iteration of this individual. If it still does not terminate, we could have carried in another iteration. We'll have to fix the maximum number of iterations. After that, if the expression does not take its terminating form, we replace all the non-terminating by the terminating symbols. The other analogy that sometimes happens, is the fact that sometimes only going up till this 9, it leaves me only with terminating symbols. it leaves me with only terminating symbols, and after that I fire any kind of rules I cannot fire, because firing of rules would require non-terminating symbols, and I have got no non-terminating symbols with me. So I cannot fire any rule. So the second anomaly comes when an expression, it gets terminated, and after that I do not fire any rules. Whenever my expression over here will consist only of terminating symbols, it will consist only of these terminating symbols, I will stop. I will not increase the pointer further, and this is the final individual that I am looking for. The other part of the individual, the other set of integers, they are not needed. Now because it's a genetic algorithm, total genetic length is constant, so I'll have to keep them, but you fill them up with any random values, it does not matter. You fill them up with any random values, it does not matter, whenever I get that all terminating condition over here. So by this simple mechanism, again revising the algorithm, I have developed a mechanism to convert the string of integers into an expression or into a program. And this program, using my own conventions, I can find out what the corresponding fitness value would be. For these examples, I can find out what the corresponding fitness value would be. So all that I have done so far is that I have converted any individual representation in this genotypic form into an expression of which I can calculate the fitness value. So I'll start off, I'll fix this total length n, I'll fix it up using my own analysis of complexity of the problem. I'll assign random numbers over it, that will make my random population. I'll use the same fundamental to calculate the fitness value of each one of them. I'll write down an stopping criterion. I'll do selection based on the fitness scaling, and the fitness scaling would ultimately be a top scaling or a rank-based scaling or a fitness-based scaling. I'll select the individual by the selection operator, I'll apply mutation crossover, I'll apply elite, I'll apply any kind of other operators that you might have. And after doing all that, I would ultimately come up with a new generation of population, and I'll keep on repeating this until the stopping criterion is met. And finally I get in the expression, I finally get in the genotypic solution which shows the best performance, which is the best program, and I can anyway convert it into a working program using the same grammar. So the crux of genetic programming is only about the use. The crux of genetic programming of grammatical evolutionary is only how can we use the notation of grammar to have an intelligent representation of an individual, to have a very clever representation of an individual, such that the grammatical part is intact, and based on a set of integers I can generate in expressions. I can generate in all kind of expressions, I can generate in all kind of programs. We'll see into the later stages when we discuss about the hybrid computing and how do we use grammatical evolution to evolve the neural network itself. The complete neural network will write down some kind of grammar, and using this grammar we'll use in a very simple genetic algorithm that is able to evolve a completely optimized neural network as a whole. And that is again a very interesting piece of work where it solves, and we'll see later what all problems that it solves when it comes to the natural evolution of the neural network. So this was about the second pillar of the evolutionary algorithm. This was about the genetic programming. We'll discuss in the last pillar, that is the evolutionary strategies. That is what will be the source of discussion for the next hour of lecture, and that is what will completely finish our domain of the evolutionary computing, and we'll directly touch upon the hybrid computing thereafter. So.